One of the lesser-known facts about me is that I'm one of the few world experts on anti-gravity. That's because 20 years ago I was convinced that repulsive gravity could explain some of the puzzling observations astrophysicists have made, which they normally attribute to dark matter and dark energy. In today's video, I'll tell you why that didn't work, what I learned from that, and also why antimatter doesn't fall up. Newton's law of gravity says that the gravitational force between two masses is the product of the masses divided by the square of the distance between them. And then there's a constant that tells you how strong the force is. For the electric force between two charges, we have Coulomb's law that says the force is the product of the charges divided by the square of the distance between them. And again, there's a constant that tells you how strong the force is. These two force laws look pretty much the same, but the electric force can be both repulsive and attractive, depending on whether you have two negative or two positive charges, or a positive and a negative one. The gravitational force, on the other hand, is always attractive because we don't have any negative masses. But why not? Well, we've never seen anything fall up, right? Then again, if there was any anti-gravitating matter, it would be repelled by our planet. So maybe it's not so surprising that we don't see any anti-gravitating matter here. But it could be out there somewhere. Why aren't physicists looking for it? One argument that you may have heard physicists bring up is that negative masses can't exist because that would make the vacuum decay. That's because if negative masses exist, then so do negative energies, because E equals mc squared and so on. Yes, that guy again. And if we had negative energies, then you could create pairs of particles with negative and positive energy from nothing, and particle pairs would spontaneously pop up all around us. A theory with negative masses would therefore predict that the universe doesn't exist, which is in conflict with evidence. I've heard that argument many times. Unfortunately, it doesn't work. This argument doesn't work because it confuses two different types of mass. If you remember, Einstein's theory of general relativity is based on the equivalence principle. That's the idea that gravitational mass equals inertial mass. The gravitational mass is the mass that appears in the law of gravity. The inertial mass is the mass that resists acceleration. But if we had anti-gravitating matter, only its gravitational mass would be negative. The inertial mass always remains positive. And since the energy equivalent of inertial mass is as usual conserved, you can't make gravitating and anti-gravitating particles out of nothing. Some physicists may argue that you can't make anti-gravity compatible with general relativity, because particles in Einstein's theory will always obey the equivalence principle. But this is wrong. Of course, you can't do it in general relativity as it is. But I wrote a paper many years ago in which I show how general relativity can be extended to include anti-gravitating matter, so that the equivalence principle only holds up to a sign. That means gravitational mass is either plus or minus inertial mass. So, in theory, that's possible. The real problem is, well, we don't see any anti-gravitating matter. Is it maybe that antimatter anti-gravitates? Antimatter is made of antiparticles. Antiparticles are particles which have the opposite electric charge to normal particles. The antiparticle of an electron, for example, is the same as the electron, just with a positive electric charge. It's called the positron. We don't normally see antiparticles around us because they annihilate when they come in contact with normal matter. Then they disappear and leave behind a flash of light, or in other words, a bunch of photons. And it's difficult to avoid contact with normal matter on a planet made of normal matter. This is why we observe antimatter only in cosmic radiation or if it's created in particle colliders. But if there is so little antimatter around us and it lasts only for such short amounts of time, how do we know it falls down and not up? We know this because both matter and antimatter particles hold together the quarks that make up neutrons and protons. Inside a neutron and proton, there aren't just three quarks. There's really a soup of particles that holds the quarks together, and some of the particles in the soup are antiparticles. Why don't those antiparticles annihilate? They do. They are created and annihilated all the time. We therefore call them virtual particles, but they still make a substantial contribution to the gravitational mass of neutrons and protons. That means, crazy as it sounds, the masses of antiparticles make a contribution to the total mass of everything around us. So if antimatter had a negative gravitational mass, the equivalence principle would be violated. It isn't. This is why we know antimatter doesn't anti-gravitate. But that's just theory, you may say. Maybe it's possible to find another theory in which antiparticles only anti-gravitate sometimes, so that the masses of neutrons and protons aren't affected. I don't know any way to do this consistently, but even so, 3 experiments at CERN are measuring the gravitational behavior of antimatter. Those experiments have been running for several years, but so far the results are not very restrictive. The alpha experiment has ruled out that antiparticles have anti-gravitating masses, but only if the absolute value of the mass is much larger than the mass of the corresponding normal particle. This means so far they ruled out something one wouldn't expect in the first place. However, give it a few more years and they'll get there. I don't expect surprises from this experiment. That's not to say that I think it shouldn't be done, just that I think the theoretical arguments for why antimatter can't anti-gravitate are solid. Okay, so antimatter almost certainly doesn't anti-gravitate. But maybe there's another type of matter out there, something new entirely, and that anti-gravitates. If that was the case, how would it behave? For example, if anti-gravitating matter repels normal matter, then does it also repel among itself, like electrons repel among themselves, or does it attract its own type? This question, interestingly enough, is pretty easy to answer with a little maths. Forces are mediated by fields, and those fields have a spin, which is a positive integer, so 0, 1, 2, etc. For gravity, the gravitational mass plays the role of a charge, and the force between two charges is always proportional to the product of those charges times -1 to the power of the spin. For a spin-zero field, the force is attractive between like charges. But electromagnetism is mediated by a spin-1 field, that's electromagnetic radiation, or photons if you quantize it. And this is why, for electromagnetism, the force between like charges is repulsive, but unlike charges attract. Gravity is mediated by a spin-2 field, that's gravitational radiation, or gravitons if you quantize it. And so for gravity, it's just the other way around again. Like charges attract and unlike charges repel. Keep in mind that for gravity, the charge is the gravitational mass. This means if there is anti-gravitating matter, it would be repelled by the stuff we are made of, but clump among itself. Indeed, it could form planets and galaxies just like ours. The only way we would know about it is its gravitational effect. That sounds kind of like dark matter and dark energy, right? Indeed, that's why I thought it would be interesting, because I had this idea that anti-gravitating matter could surround normal galaxies and push in on them, which would create an additional force that looks much like dark matter. Normally, the excess force we observe is believed to be caused by more positive mass inside and around the galaxies. But aren't those situations very similar? More positive mass inside or negative mass outside pushing in? And if you remember, the important thing about dark energy is that it has negative pressure. Certainly, if you have negative energy, you can also get negative pressure somehow. So, using anti-gravitating matter to explain dark matter and dark energy sounds good at first sight. But at second sight, neither of those ideas work. The idea that galaxies would be surrounded by anti-gravitating matter doesn't work because such an arrangement would be dramatically unstable. Remember, the anti-gravitating stuff wants to clump just like normal matter. It wouldn't enclose galaxies of normal matter. It would just form its own galaxies. So getting anti-gravity to explain dark matter doesn't work even for galaxies, and that's leaving aside all the other evidence for dark matter. And dark energy? Well, the reason that dark energy makes the expansion of the universe speed up is actually not that it has negative pressure. It's that the ratio of the energy density over the pressure is negative. And for anti-gravitating matter, they both turn negative, so that the ratio is the same. Contrary to what you expect, that does not speed up the expansion of the universe. Another way to see this is by noting that anti-gravitating matter is still matter and behaves like matter. Dark energy, on the contrary, does not behave like matter, regardless of what type of matter. This is why I get a little annoyed when people claim that dark energy is kind of like anti-gravity. It isn't. So, in the end, I developed this beautiful theory with a new symmetry between gravity and anti-gravity. And it turned out to be entirely useless. What did I learn from this? Well, that I wasted a considerable amount of my time on this was one of the reasons I began thinking about more promising ways to develop new theories. Clearly, just guessing something because it's pretty is not a good strategy. In the end, I wrote an entire book about this. Today, I try to listen to my own advice at least some of the time. I don't always listen to myself, but sometimes it's worth the effort. This video was sponsored by Brilliant. Whether or not you believe that anti-gravitating matter exists, it's fun playing around with the idea what you could do with it if it exists. And it's really basic physics. If you want to freshen up your knowledge about physics or learn something new, Brilliant is a great place to start. Brilliant is a website and app that offers interactive courses on a large variety of topics in science and mathematics. I love their courses because they are so to the point and they allow you to explore the depth of each topic on your own. For more background on the physics I talked about today, check out Brilliant's courses on classical mechanics and gravitational physics. All their courses will challenge you with questions so you can check your understanding along the way. To support this channel and learn more about Brilliant, go to brilliant.org/Sabine and sign up for free. The first 200 subscribers using this link will get 20% off the annual premium subscription. Thanks for watching. See you next week.